Captain Mike Landry nearly failed to take the call when it was received on a Tuesday morning in late June of 2019. His John boat was idling against a stand of bald cypress, and he was already 2 hours into the Atchafalaya Basin, looking at something that had no right to be there. The bayou that he had been running since he was 14, the same one that his father and grandpa had run before him, had vanished. In its place sat a solid platform of purple-flowered green, stretching bank to bank as far as the headlamp reached, dense enough that a man could have walked across it without wetting his boots. He had seen water hyacinth before, but nothing like this. Nothing that looked less like a plant and more like the bayou had simply ceased to exist. He killed the motor. The silence that followed was not the good kind. Not frog song and heron calls and the soft splash of a surfacing bass. This was the silence of absence. Mike Landry had worked the Atchafalaya for 31 years, the largest river swamp in North America. It had survived oil booms, hurricanes, and federal flood control projects that rerouted the entire lower Mississippi system, and now it was losing to a floating flower. He called a retired federal researcher named James, a biologist who'd spent 30 years working invasive aquatic species. The old man listened, then said something Mike couldn't shake loose. "I've walked parts of the Amazon where that plant grows wild. You know what it looks like there?" A pause. "Like a plant. Just a plant. One plant among thousands." That sentence sat in Mike's chest like a fishhook, because it raised a question with no obvious answer. If water hyacinth evolved in the Amazon, why didn't the Amazon look like this bayou? Water hyacinth arrived in the United States with the best possible intentions, which is often how the most destructive things travel. At the 1884 World's Industrial and Cotton Centennial Exposition in New Orleans, Brazilian exhibitors displayed a collection of ornamental plants. Among them was a floating aquatic flower with glossy leaves and lavender blooms, so striking that American visitors began requesting cuttings almost immediately. Within a decade, the plant had been distributed across the South as a decorative addition to garden ponds. Nobody asked what it did when nobody was watching. By 1897, water hyacinth had already clogged the St. Johns River in Florida so severely that commercial steamboat traffic was disrupted. Congress authorized the Army Corps of Engineers to address the problem. The Corps deployed mechanical cutters, chemical treatments, burning. Within 2 years, the hyacinth had returned everywhere it had been removed. Within a generation, it had colonized hundreds of miles of Florida waterways, spread across Louisiana's bayou systems, and begun advancing up the Texas Gulf Coast. The question of how to stop it had become one of the most expensive and persistent problems in American freshwater management. The numbers are staggering. Annual management costs across the southern United States exceed $150 million. In Florida alone, the state has spent hundreds of millions over 5 decades on herbicide programs, mechanical harvesting, and biological control research. Yet hyacinth remains a perennial presence in Lake Okeechobee and the northern Everglades. In Louisiana, the invasion has been described as functionally permanent, not a crisis to be solved, but a condition to be managed indefinitely. Water hyacinth now affects more than 50 countries on 6 continents, making it one of the most costly freshwater invasive species in recorded history. To understand why, you have to understand what the plant actually does when left alone in North American water. Water hyacinth is not simply a nuisance, it is an ecological transformer. A single plant, under ideal conditions, can produce a daughter plant within 2 weeks. Within a growing season, a small colony can cover an acre of open water. Within a few years, It can close off an entire navigational channel, shade out every submerged plant beneath it, and drive dissolved oxygen low enough to suffocate fish. On the Atchafalaya in a bad summer, mats have stretched for miles. On Lake Okeechobee, infestations have covered tens of thousands of acres simultaneously, disrupting flood control infrastructure that protects millions of South Florida residents. What makes it so effective is precisely what made it attractive in 1884. It grows on the surface, in open sunlight, with its roots hanging freely in the water column. It needs nothing to anchor it. It competes with nothing until it wins. And yet, none of this happens in the Amazon. In the summer of 2007, a team of researchers from the USDA Agricultural Research Service traveled to the Várzea, the seasonally flooded forests along the Middle Amazon River in Brazil. Their local guide, Eduardo, led them to a shallow lagoon edged with palms and said simply, "Ah, the water lettuce cousin. Yes, it's everywhere. Look." It was everywhere, floating in clusters along the shoreline, drifting in open water, tucked into the shallows. Water hyacinth, the same species burying the Atchafalaya and choking Lake Okeechobee, growing here in casual abundance as if it had never heard of conquest. Dr. Ted D. Center had spent 20 years at the USDA Aquatic Weed Research Laboratory in Fort Lauderdale. His work had produced significant early insights into biological control, including documentation that two small weevils, Neochatina eichhorniae and Neochatina brucci, could suppress hyacinth growth when introduced into infested waterways. But the Amazon expedition was something different. Center and his colleagues weren't visiting to collect more insects. They were visiting to understand why the insects worked at home in a way they only partially replicated abroad. What they found over the following weeks reshaped a generation of invasive species research. The weevils were there, as expected, but they were not alone. Working slowly through the hyacinth colonies, the team documented a community of interacting organisms that made the North American situation look like a fundamentally different ecological equation. There were at least 7 specialist moth species whose larvae fed exclusively on water hyacinth tissue, several of them completely unknown to North American science at the time. There were fungal pathogens leaving characteristic lesions on leaf surfaces, subtle discolorations that, on closer examination, proved to be the entry points of organisms that had evolved specifically to exploit damage left by insect feeding. There were mites, there were thrips, there were nematodes in the root tissue, and there were fish. Several species of small cichlids and characins recorded feeding directly on hyacinth root systems and consuming the invertebrates sheltering among them. None of these organisms killed the plant outright. That was the revelation. Not one of them in isolation could control an infestation, but together, operating simultaneously on every surface and tissue throughout the growing season, they produced something the researchers could only describe as chronic stress. The plant was never healthy in the Amazon. It was always healing, always recovering, always diverting energy from growth into tissue repair. We had been thinking about this as a predator-prey problem, Center said in a 2011 paper. One agent, one target. But the Amazon showed us something more like a committee. Nobody chairs the meeting. Nobody has to. The weevils had arrived in American water in 1972, introduced by USDA researchers after years of host specificity testing. The initial results were encouraging. In Florida test sites, hyacinth cover declined measurably. Researchers reported reduced plant density, smaller leaves, and increased susceptibility to the fungal pathogen Cercospora pieropi. By the late 1980s, some infested waterways were showing genuine recovery, with native plants recolonizing areas sealed beneath hyacinth mats for years. Then the system began to show its limits. In high-nutrient waterways, lakes and rivers receiving agricultural runoff, suburban stormwater, or sewage discharge, the weevils simply could not keep pace. Water hyacinth fed on nitrogen and phosphorus, the way a fire feeds on oxygen, and Florida's waterways had been receiving elevated nutrient loads for decades. The plant grew faster than the weevils could damage it. Chemical herbicide programs, renewed through the 1990s and 2000s, were still necessary. They remain necessary today. The Amazon team's findings offered a partial explanation. The missing organisms, the specialist moths, the co-evolved fungal pathogens, the root-feeding fish, the mites, represented decades of additional suppression that North American waterways simply did not have. Restoring 2 weevil species to an ecosystem that had lost 30 co-evolved partners was like repairing a clock by replacing 1 gear. But there was something else. In the Amazon, water hyacinth never grew in the nutrient concentrations typical of American-managed waterways. The open water where hyacinth floated was not enriched by sewage or agricultural runoff. The ecological community suppressing it had evolved alongside a plant that was already nutritionally constrained. When hyacinth escaped to North American water, supercharged with nutrients from a century of industrial agriculture and urban development, it gained not just freedom from its enemies, but a food source its evolutionary history had never prepared its enemies to compensate for. The invasion had 2 engines. The absence of natural enemies was one. The presence of unnatural nutrient loading was the other. Both had to be addressed. Neither had been, systematically, anywhere. A University of Florida graduate student discovered something in October 2016 that her advisor first believed to be a data mistake. She had introduced weevils into a hyacinth colony maintained at low nutrient levels in an experimental pond in Gainesville, simulating a Florida spring-fed river prior to contemporary agricultural phosphorus loading. Weevils were introduced to the control pond, which was the same size, in water with nutrient levels similar to modern Lake Okeechobee. After 18 months, the difference was not subtle. In the low-nutrient pond, the weevil population had grown to more than 4 times its initial size. Hyacinth cover had dropped by 63%, and native aquatic plants had recolonized the open water on their own. In the high-nutrient pond, hyacinth cover had decreased by less than 15%, and no native recovery was observed. The student, Camille, had accidentally reconstructed the biochemistry of the Amazon, not its species community, but its baseline conditions. And in those conditions, even 2 introduced weevils were enough to tip the balance. The paper that followed, published in 2018, made a quiet but radical argument. Biological control was not failing because the introduced organisms were ineffective. It was failing because the waterways had been transformed in ways that systematically favored the invader over its enemies. The biological agents were performing as designed, inside an environment redesigned to work against them. Today, the Atchafalaya Basin receives millions of dollars annually in herbicide and mechanical control spending. The Louisiana Department of Wildlife and Fisheries, the Army Corps of Engineers, and several parish governments maintain overlapping treatment programs representing one of the largest aquatic weed management operations in American history. Airboat crews work from spring through fall. Amphibious harvesters cut biomass by the ton. Herbicide aircraft fly low over Cypress and Tupelo, marking treatment zones with GPS precision. The result is not a solution. It is a maintenance schedule. Mike Landry knows the schedule well. In a good year, the crews stay ahead of the growth, and his bayous remain navigable through summer. In a bad year, after a warm, wet winter, or a flood pulse that spreads seed banks into new areas, entire sections of his regular water become inaccessible for weeks. His business, built around the knowledge of a specific landscape, periodically becomes knowledge of a landscape that no longer exists in the form he learned it. "I don't begrudge the crews," he said one evening, watching a treatment airboat work a distant cut. "They're doing what they can. It's just that what they can do isn't enough." What might be enough is something researchers are still assembling: additional biocontrol agents, including a specialist moth documented in the Amazon survey, have undergone host specificity testing, and several are under consideration for release. Water quality restoration programs in Florida are attempting, at enormous cost, to reduce phosphorus inputs to Lake Okeechobee. Early data from restored marshes show reduced hyacinth pressure where nutrient levels have declined. A growing body of research is also exploring the cascade of co-evolved relationships the plant carries, the microbial communities, fungal associations, and subtle ecological architecture that its Amazon partners exploited for millions of years. None of this is fast. The Amazon did not assemble its regulatory community around water hyacinth in a century. It assembled it across evolutionary time, millions of years of mutation, counter-adaptation, and small adjustments between plant and enemy, until the relationship reached something close to equilibrium. Reconstructing even a fraction of that in a managed American waterway is the work of generations. There is a moment, somewhere in the middle of a long day on the Atchafalaya, when the light drops low enough to turn the water the color of old copper, and the cypress knees cast shadows like the legs of something enormous walking just beneath the surface. In that light, the hyacinth mats lose their menace. The lavender flowers, the same flowers that charmed a New Orleans exhibition hall in 1884, catch the last horizontal sun and glow with the kind of beauty that probably explains everything about how this started. It is not a malevolent plant. There is no such thing. It is a plant lifted out of the only world it had ever known, the only world its enemies knew, and carried across an ocean to a place where none of the million small pressures that had always kept it ordinary had ever existed. It did what any living thing does when the constraints disappear. It expanded. The question researchers carry out of the Amazon and back into American waterways is not how to destroy it. Eradication, for a plant this established across a landscape this large, is not a realistic goal. The question is whether it's possible to restore enough of what was lost, enough of the invisible network of pressure and counterpressure that constituted its true ecological home, to bring it back into something resembling balance. The weevils are out there, working in the dark beneath the mats, their larvae tunneling through petioles in silence, weakening something vast with patient, evolutionary purpose. The fungal pathogens follow the feeding wounds. The weakest plants sink first, in experimental ponds and recovering marshes, and carefully managed restoration sites. The water is slowly beginning to remember what it was before a beautiful flower from the Amazon decided, without any intention at all, to become an island. Whether the rest of the system, the nutrient chemistry, the missing species, the evolutionary relationships still waiting in a South American floodplain, can be imperfectly reassembled in time to matter, is a question that will be answered not in laboratories but in the slow language of ecosystems, which measure time in ways humans find difficult to read. Mike Landry still runs the Atchophilia. He knows which channels are clear and which ones aren't, and he has learned to read the hyacinth the way his grandfather read the weather, not as a problem to be solved, but as a condition to be understood. Last spring, in a backwater he had written off 2 seasons before, he found open water, maybe 100 yards of clear surface, dark and still, with a great blue heron standing in it up to its knees like it had always been there. He cut the motor and drifted for a while, not fishing, just watching. He didn't know if the weevils had done it, or the herbicide crews, or just the odd physics of a drifting mat. Maybe it didn't matter. The water was there. The heron was there. Somewhere beneath the surface, the old relationships between water and plant, between predator and prey, between a landscape and everything that had shaped it, were still trying to find each other. Nature rarely announces its discoveries. It simply makes them, quietly, in the places we haven't thought to look yet.